Chapter 1, Reflection of Light at Curved Surfaces. In class 7 and 8, you learned about the image formation in plane mirrors. You also discussed about the spherical mirrors. You know that why the curved surfaces are known as spherical mirrors. You might have got many doubts while observing your image in bulged surfaces. Is the image formed by a bulged surface same as the image formed by a plane mirror? Is the mirror used in automobiles a plane mirror? Why it is showing small images? Why does our image appear thin or bulged out in some mirrors? Can we see inverted image in any mirror? Can we focus sunlight at a point using a mirror instead of a magnifying glass? Are the angle of reflection and angle of incidence also equal for reflection by curved surfaces? Let us discuss about the reflection of light by spherical mirrors in this lesson to get clarity for the above questions. Reflection of light by spherical mirrors. The first law of reflection tells us a light ray incident at an angle with the normal at the point of incidence will get reflected making equal angle with the normal. This law is true for all surfaces, be it a plane surface or a curved one. The important words here are the angle made with normal at the point of incidence. If for any surface one can decide the normal and find the incident angle, it is possible to deduce the angle made by the reflected ray. It is very easy to find a normal at any point on plane surface, but for a curved or uneven surface, it is not straightforward. Activity 1. Finding the normal to a curved surface. Let us take a small piece of thin foam or rubber, like the sole of a slipper. Put some pins along a straight line on the foam as shown in the figure 1a. All these pins are perpendicular to the plane of foam. If the foam is considered as a mirror, each pin would represent the normal at that point. Any ray incident at that point where the pin makes the contact with the surface will reflect with the same angle as the incident ray made with the pin normal. Now bend the foam piece inwards as shown in the figure 1b. What happens to the pins? They still represent the normal at various points, but you will notice that all the pins tend to converge at a point or intersect at a point. If we bend the foam piece outwards, we will see that the pins seem to move away from each other, or in other words, they diverge as shown in the figure 1c. This gives us an idea of what is likely to happen with a spherical mirror. A concave mirror will be like a rubber sole bent inwards, figure 1b, and the convex mirror will be like the rubber sole bent outwards, figure 1c. For a concave mirror like these pins in figure 1b, all normals will converge towards a point. This point is called center of curvature of mirror. Recall a little bit of geometry. While learning about circles and tangents, you have learned that a radius is always perpendicular to the tangent to the circle drawn at the point. This gives us a clue about how we can find normal to any point on a spherical mirror. All that we have to do is to draw a line from the point on the mirror to the center of the sphere. It is much easier to imagine this in a two-dimensional figure as shown in figure 2a. The concave mirror is actually a part of a big sphere. In order to find its center point, center of curvature, we have to think of the center of sphere to which the concave mirror belongs. The line drawn from C to any point on the mirror gives the normal at that point. For the ray R, the incident angle is the angle it makes with the normal, shown as I, and the reflected angle is shown as R in figure 2b. We know by first law of reflection I is equal to R. The midpoint, geometrical center of the mirror, is called pole of the mirror. The horizontal line shown in figures which passes through the center of the curvature and pole is called principal axis of the mirror. The distance between P and C is radius of curvature of the mirror. Try to construct different reflected rays for any array of rays that are parallel to the principal axis as shown in the figure 2b. What is your conclusion? Verifying your drawing with experiment. To verify this, we must first find out some way of obtaining a beam of parallel rays. How do we do that? First, we need to create a situation in which one gets parallel rays of light. In figure 3, we have stuck two pins on a thermocol block. The pins are parallel to each other. As we see in the figure, when a source of light is kept very near, we see shadows diverging from the base of the pins. As we move the source away from the pins, the angle of divergence gets reduced. If we move the source far away, we will get parallel shadows. But as we move the candle away, the light intensity becomes low. That means to get a beam of parallel rays, the source should be at a long distance and it must be of sufficient intensity. Where do we find one such source? Yes, we have one easily available source. You probably have guessed it, the sun. Let us do an experiment with sun rays and a concave mirror. Activity 2. Hold a concave mirror such that sunlight falls on it. Take a small paper and slowly move it in front of the mirror and find out the point where you get the smallest and brightest spot, which will be the image of the sun. See to it that your paper is small so that it does not obstruct the incoming sun rays. The rays coming from the sun parallel to the principal axis of concave mirror converge to a point, see figure 4. This point is called focus or focal point of the concave mirror. Measure the distance of this spot from the pole of the mirror. The distance is called focal length of the mirror. The radius of curvature will be twice this distance. R is equal to 2f. Does this help you to verify the conclusions you arrived at with your drawing? What happens if you hold the paper at a distance shorter than the focal length from the mirror and move it away? Does the image of the sun become smaller or bigger? You will notice that the image of the sun first keeps on becoming small. Beyond the focal point, it keeps on becoming enlarged. Note: while drawing a ray diagram, sometimes it is not clear which is the reflecting side of the mirror. Hence, we follow a convention of showing lines on the non-reflecting side, quoted side. Can you draw the same diagram for a convex mirror? See figure 5. The parallel rays appear to diverge after reflection. If we extend the reflected rays backwards, they meet at F, that is, focus of the convex mirror. Think and discuss. See figure 5. A set of parallel rays are falling on convex mirror. What conclusions can you draw from this? Will you get a point image if you place a paper at the focal point? When parallel rays are incident on a concave mirror on reflection, they meet at the focus. Do we get an image with a concave mirror at the focus every time? Let us find out. Lab activity. Lab activity. Aim. Observing the types of images and measuring the object distance and image distance from the mirror. Material required. A candle, paper, concave mirror, known focal length. V-stand, measuring tape or meter scale. Procedure. Place the concave mirror on V-stand. Arrange candle and meter scale as shown in the figure 6. Keep the candle at different distances from the mirror, 10 centimeters to 80 centimeters, along the axis, and by moving the paper screen, find the position where you get the sharp image on paper. Take care that flame is above the axis of mirror, paper is below the axis. Note down your observations in table 1. Distance of candle from mirror, object distance, distance of paper from mirror, image distance, enlarged or diminished, inverted or erect. Group your observations based on the type of image you see. Example, image is bigger and inverted. It is possible you may not get any image at some positions. Note down that too. Since we know the focal point and the center of curvature, we can reclassify our above observations as shown in the table 2. What do you infer from this table? At this point, we suggest that you make one more observation. You have been trying to get the image on a paper when the object is at different positions. At the same time, also look into the mirror and note your observations about how the image appears. Is it inverted or erect, enlarged or diminished? Position of the candle, that is object. Position of the image, enlarged or diminished, inverted or erect, real or virtual. Position of the candle between mirror and F at focal point, between F and C at center of curvature, beyond C. What do you infer from the table 2? Let us try to draw ray diagrams with concave mirrors and compare them with your inferences. Ray diagrams for concave mirror. In activity 5, we saw the ray diagram of sun rays parallel to the concave mirror, and the image of the sun was very small at the focal point. See figure 4. Now we shall develop a technique to draw ray diagrams when an object is placed anywhere on the axis of the mirror and validate the above observations. Here we will take at least two rays originating from the same point on the object but with different direction. See how they get reflected from the mirror and find out point where they meet to form the image. Let us take an example. As shown in the figure 7, assume a concave mirror and a candle placed at some distance along the x-axis of the mirror. The diagram shows two rays coming from the tip of the flame object. The reflected rays are constructed based on the laws of reflection. They meet at point A. The tip of the flame of reflected image will be at the point of intersection A. Why only at point A? If we hold the screen at any point before or beyond point A, for example at point B, we see that the rays will meet the screen at different points. Therefore, the image of the tip of the flame will be formed at different points due to these rays. If we draw more rays emanating from the same tip, we will see that at point A they will meet, but at point B they won't. So the image of the tip of the flame will be sharp if we hold the screen at point A, and will become blurred due to overlapping of multiple images when we move the paper slightly in any direction forward or backward. Is this not something that you observed during the previous experiment with sun rays? However, it is not going to be easy to evaluate the angle of reflection for any arbitrary ray. Every time we will have to find the normal, measure the incident angle, and construct a ray with equal angle on the other side. This would be a tedious task. Can we find any other simpler method? Yes, there are a few. Based on our discussion so far, we can identify some appropriate rays which we can take as representative rays to find the point A. We have seen that all rays that are parallel to the axis get reflected such that they pass through the focal point of the mirror. So, for drawing any diagram, the most suitable ray to draw will be the one that comes from the object and goes parallel to the axis of the mirror. The reflector ray will be the line drawn from the point of incidence on the mirror and passes through the focal point of the mirror. To make it more convenient, we will always take rays that come from the tip of the object. See the ray R1 in figure 8. The converse situation of previous one is also true. That is, a ray that passes through the focal point of the mirror will travel parallel to the axis after reflection. This gives us our second ray. This will be the ray coming from the tip of the flame and going through the focal point and falling on the mirror. After reflection, this ray travels parallel to the axis, so we draw the reflected ray as a parallel line to the axis coming from the point where the incident ray meets the mirror. See R2 in figure 9. Using the rays R1, R2 and finding the point where they intersect, we know the point where the image of the tip is formed. There is one more ray which is convenient to draw. We have seen earlier that any ray that is normal to the surface on reflection will travel along the same path but in the opposite direction. Which ray can such a one be for a spherical mirror? We know that a line drawn from the center of curvature to the mirror is perpendicular to the tangent at the point where the line meets the curve. So, if we draw a ray coming from the tip of the object going through the center of curvature to meet the mirror, it will get reflected along the same line. This ray is shown as R3 in figure 10. In general, a ray traveling along normal retraces its path. Along with these three rays, the ray which comes from the object and reaches the pole of the mirror is also useful in drawing ray diagrams. For this, the principal axis is the normal. If we have our object placed as shown in the figure 11, We can draw the ray diagram to get the point of intersection A of any two rays coming from the top of the object and point of intersection B of any two rays coming from the bottom of the object. We notice that point B is exactly at the same distance from the mirror as point A. Hence the image is vertical and inverted. Where is the base of the candle expected to be in the image when the candle is placed on the axis of the mirror? Since any ray coming from any point on the axis and traveling along the axis will get reflected on the axis itself, we conclude that the base of the image is going to be on the axis. Using the knowledge that if the object is placed vertically on the axis, the image is going to be vertical, all that we need to do is to draw a perpendicular from point A to the axis. The intersection point is the point where the base of the image of the candle is likely to be formed. See figure 12. Hence, as shown in the diagram, the image will be inverted and diminished. Figure 12 is drawn for the case where the object is placed beyond the center of curvature. Does this conclusion match with your observations? Lab activity. Draw similar diagrams for other cases and verify that they match with your observations. During the experiment, did you get any positions where you could not get an image on the screen? Consider the case shown in the figure 13. The candle object O is placed at a distance less than the focal length of the mirror. The first ray R1 will start from the tip of the object and run parallel to the axis to get reflected so as to pass through the focal point. This one is easy to draw. The second ray that we chose for earlier ray diagrams is the ray coming from the tip of the object and going through the focal point, but it is not possible as such a ray will not meet the mirror. So we must use the third ray, a ray coming from the tip of the object and going through the center of curvature. But the two does not seem to be possible, so we make a small change. Instead of drawing a ray from the candle tip to the center of curvature, we consider a ray that comes from the tip and goes in such a direction that it would go through the center of curvature if extended backwards. This ray is normal to the surface and so will be reflected along the same line in opposite direction and will go through the center of curvature. We notice that the two reflected rays, figure 13, diverge and will not meet. While doing the experiments for a case such as this, we are unable to find any place where we get a sharp image on the screen. This ray diagram tells us that since the reflected rays are diverging, we will not get an image anywhere. So, even if we had moved the screen much away from the mirror, we would not have found an image. In such situations, however, we do see an image when we look in the mirror. Is it possible to explain this image with a ray diagram? Remember what we did to find the image in the mirror. To decide the position of image, we extended the reflected rays backwards till they meet. We will do the same here. When we look in the mirror, we are looking at these diverging reflected rays. They appear to be coming from one point. We can get this point by extending the rays backwards as shown in the figure 14. The image does not really exist the way we see in other cases, but it is visible to us. As seen in the figure 14, the image will be erect and enlarged. Does this match with your observations? This image that we get by extending the rays backwards is called an virtual image. We cannot get this on a screen like a real image. The case in which the object is at the center of curvature is another interesting situation. See figure 15. From the ray diagram figure 15, we conclude that the image of the object will be formed at the same distance as the object and it will be inverted and of the same size. What is your observation? Think and discuss. Do you get an image when the object is placed at F? Draw a ray diagram to the experiment. From the ray diagrams and the observations, you may have noticed some peculiar properties of concave mirrors. They enlarge the image when the object is held close to the mirror less than the focal length. Also, the image is erect. This property is used at many places and most commonly in shaving mirrors and mirrors used by dentists. Another property is the way that it can converge the rays to its focal point. This is extensively used in many places. Look at the shape of TV, dish antennas. If you look around, you will see many curved surfaces, but all surfaces are not concave. Many of these are convex. Have you observed the rear view mirror of a car? What type of surface do they have? Have you observed images formed on the rear window glasses of a car? What type of surfaces are these? See figure 16. Can we draw ray diagrams for convex surfaces? Ray diagrams for convex mirrors. One can draw ray diagrams for a convex mirror too. The easy rays that we identified earlier can be used in this case with small modification. Here there are three rules which describe these rays. The procedure for drawing the diagram is similar and is not repeated here. Rule 1. Any ray parallel to the axis on meeting the convex mirror will get reflected so as to appear as if it is coming from the focal point. See figure 17. Rule 2. This is converse of rule 1. A ray traveling in the direction of the focal point after reflection will become parallel to the axis. See figure 18. Rule 3. A ray traveling in the direction of the center of curvature will, on reflection, travel in the opposite direction and appears to be coming from the center of curvature. See figure 19. Now let us use these rules to show the formation of images when the object is placed at different places in front of the convex mirror. See figure 20. AB is the object placed at any point on the principal axis in front of the convex mirror. Using rule 1 and rule 3, we get an erected, diminished and virtual image between P and F on the backside of the mirror. This image cannot be caught on the screen and visible only in the mirror. Hence, this is a virtual image. Verify this with an experiment. Using these rules, draw ray diagrams to show formation of images when an object is placed at different positions and note down your conclusions. Verify your results experimentally. You may get the image at a particular distance when you place the object at a certain distance. Do you find any relation between the object distance u and the image distance v? Derivation of formula for curved mirrors. Observe figure 21. The ray from the tip B of the object AB is emanating parallel to the principal axis and striking the mirror at X. This ray passes through F after reflection. Another ray starting from B passes through the center of curvature and strikes the mirror at Y. This ray returns back in the same direction after reflection. Their two rays xb dash and yb dash are meeting at b dash. So b dash is the image of B. Hence the image of AB is A dash B dash. From the figure above 21, triangle ABC and triangle A dash B dash C are similar triangles. AB by A dash B dash is equal to AC by A dash C. Draw a line XP dash perpendicular to the principal axis. Similar triangle P dash XF and triangle A dash B dash F are similar triangles. P dash X by A dash B dash is equal to P dash F by A dash F. Equation 2. From the figure 21, we can say that P dash X equal to AB. AB by A dash B dash is equal to P dash F by A dash F. Equation 3. From the equations 1, 3, we can write AC by A dash C equal to P dash F by A dash F. Equation 4. If the paraxial rays which are traveling very near to the principal axis are considered, we can say that P dash coincides with P. Then P dash F equal to PF. AC by A dash C equal to PF by A dash F. Equation 5. We can observe from figure 21 that AC equal to PA minus PC, A dash C equal to PC minus PA dash, A dash F equal to PA dash minus PF. By substituting these in equation 5, PA minus PC divided by PC minus PA dash equal to PF divided by PA dash minus PF. Equation 6. We know that PA equal to U, PC equal to R equal to 2F, PA dash equal to V, PF is equal to F. U minus 2F by 2F minus V equal to F divided by V minus F. U minus 2F into V minus F equal to F into 2F minus V. UV minus UF minus 2F plus 2F square is equal to 2F square minus VF. UV equal to 2F square minus VF plus UF plus 2VF minus 2F square. UV is equal to UV plus VF. Divide equation 7 with UVF. UV divided by UVF equal to UF divided by UVF plus VF divided by UVF. 1 by F is equal to 1 by V plus 1 by U. The relation is 1 by F is equal to 1 by V plus 1 by U, which is known as mirror formula. While using this formula, we have to use sign convention in every situation. Sign convention for the parameters related to the mirror equation. All distances should be measured from the pole. The distances measured in the direction of incident light to be taken positive, and those measured in the direction opposite to the incident light to be taken negative. Height of the object h0 and height of the image hi are positive if measured upwards from the axis and negative if measured downwards. Now let us understand magnification. That is, the relation between the size of the object and the size of the image. The image formed by a spherical mirror varies in size. Here we discuss the variation in height only. Observe figure 22. A ray coming from O dash is incident at pole with an angle of incidence theta and get reflected with same angle theta. From figure 22, we can see that triangle POO dash and triangle PII dash are similar triangles. So II dash by OO dash is equal to PI by PO. Equation 1. According to sign convention, PO is equal to minus U, PI is equal to minus V, O dash is equal to H naught, I dash is equal to HI. Substituting the above values in equation 3, minus HI by H naught equal to minus V by minus VU, HI by H naught is equal to minus V by U. Therefore, magnification M is equal to Hi by H naught equal to minus V by U. We define the magnification. M is equal to height of the image by height of the object. In all cases, it can be shown that M is equal to minus of image distance by object distance U. Calculate the magnifications of the with the information you have in table 2 for all the 5 cases. Example, an object 4 cm in size is placed at 25 cm in front of a concave mirror of focal length 15 cm. At what distance from the mirror would a screen be placed in order to obtain a sharp image? Find the nature and the size of the image. Solution. According to the sign convention, focal length f is equal to minus 15 centimeters. Object distance u is equal to minus 25 centimeters. Object height h naught is equal to plus 4 centimeters. Image distance v is equal to how much? Image height hi is equal to how much? Substitute the above values in the equation. 1 by f is equal to 1 by u plus 1 by v. 1 by minus 15 is equal to 1 by v plus 1 by minus 25. That gives 1 by v is equal to 1 by 25 minus 1 by 15. 1 by v is equal to minus 2 divided by 75. V is equal to minus 37.5 centimeters. So the screen should be placed at 37.5 centimeters from the pole of the mirror. The image is real. Magnification m is equal to hi by h naught equal to minus v by u. By substituting the above values, hi by 4 is equal to minus 37.5 divided by minus 25. Hi is equal to minus 37.5 into 4 divided by 25. Hi is equal to minus 6 centimeters. So the image is inverted and enlarged. We have learned the phenomena of reflection of light by curved mirrors. Let us make use of it in our daily life. Making of solar cooker. You might have heard the story of Archimedes burning ships using mirrors. Can we at least heat up a vessel using a mirror? Let us try. We have already learned that a concave mirror focuses parallel sun rays at the focal point of the mirror. So, with a small concave mirror, we can heat up and burn paper as shown in the figure 23. Try this with convex mirror also. What do you observe? In the same way, make a big concave mirror to heat up a vessel. You might have observed the dish antenna. Make a wooden or iron frame in the shape of TV dish. Cut acrylic mirror sheets into 8 or 12 pieces in the shape of isosceles triangles with a height equal to the radius of your dish antenna. The bases of 8 or 12 triangles together make the circumference of the dish. Stick the triangle mirrors to the dish as shown in the figure 24. Your solar heater or cooker is ready. Arrange it so that the concave part faces sun. Find its focal point and place a vessel at that point. The vessel gets heated enough to cook rice. In practical applications, like in car headlights, concave mirrors are of parabolic shape. See figure 25. Keywords: center of curvature, radius of curvature, principal axis, pole, focus or focal point, focal length, object distance, image distance, virtual image, real image, magnification. What we have learnt: normal to the curved surface at a point on it is the line joining the center of curvature and that point. Mirror formula: 1 by f is equal to 1 by v plus 1 by u. Magnification: m is equal to size of the image by the size of the object is equal to hi by h naught, or m is equal to minus of image distance by object distance is equal to minus v by u. The image formed by actual intersection of reflection rays is called real image. This can be caught on screen. The image formed by controlled rays of reflection is called virtual image. It cannot be caught on screen. Position of the candle between mirror and f. The position of the image will be behind the mirror. Enlarged image, erect, and virtual image will be formed. When the position of the candle is on focal point, position of the image will be formed at infinity. When the position of the candle is between F and C, beyond C that will be the position of the image. Enlarged, inverted and real image will be formed. When the position of the candle is on center of curvature, position of the image will be at C with same size, inverted and real image. When the position of the candle is beyond C, The position of the image will be between F and C. Diminished, inverted and real image will be formed. When the position of the candle is at infinity, the position of the image will be at focus and a point-sized real image will be formed.